Okay, so you're turning in homework 3, correct? And we can talk about the afterwards. How's it going? What's going for you? Not enough time in the day. Okay, time management skills. That's good. Anything else? Health. Yeah, that's, not being indestructible is always really tough. Yeah. Everyone getting their flu shots and everything? Preventative care? Oh my gosh. All right, well, let's go get our flu shots this weekend and then we're gonna feel safe in spring. If it's an alliteration, then it's true, right? Safe in spring. Okay. You know what alliteration is? Alliteration is like when the first two letters of safe in spring, like a saying, like have repeated first letters that are the same. That's called alliteration. We're gonna learn some words, okay? So get used to word learning. We were talking about kinematics, right? And part of the things that we talked about were using streamlines and streak lines and path lines. How are those related? What is a path line?
Well, I actually didn't put on the curve, I decided that curve that represents the flow direction.
So that would be your streamline. Yeah, what's a path line?
Oh, sorry. Actually followed by an individual particle over time.
Exactly, right? So we watch one single piece of fluid and we watch it go through. And we're comfortable saying piece of fluid now, right? Good. And what about a streak line?
There's curves formed by adjacent particles that pass through a particular point.
Right. So that's two ways of looking at the same thing, right? The path line describes a single parcel of fluid and all the space that it goes through. And a streak line represents a single spot and all the parcels that go through it, right? Okay. So we need to finish this discussion of kinematics before we can do the fun stuff, right? Because kinematics by definition does not include any forces. We haven't discussed why anything is happening, but we have to set up all of the mathematics that we're going to use in order to properly discuss fluids. And then once we get into conservation laws and getting to write down the very first fluid equations, then we'll be able to understand where they're coming from. So we'll start using them in physical contexts, right? So we'll think of them in terms of what do waves on the ocean look like? What do waves on a planetary scale look like, right? Well, there's a little bit of time to get there. The first thing that we were talking about here was how we just described flows. So on the left-hand side, you see an example of a vortex. What type of vortex is this on the left? What does the word vortex mean, by the way? Vacuums, they suck, right? So that is not always a great description for fluids here, right? So for example, we might, in practice, make one of these by having a hole, but that doesn't necessarily mean that this is a vortex.
Something to do with rotational?
Good. Yeah, something about rotation, right? Okay, something about rotation. Good. So the one on the left is what we call solid body rotation. What do I mean by that? It's a fluid, right? Can you give me an example of solid body rotation? If I spin in a circle? Sure, okay, that might work. I'm certainly a solid body, but that's not what I meant by this. I gave an example when we presented this in class. Let's look at this parcel, right? So I have the edges of the parcel, A, B, C, D. As they move around in the fluid, how do they deform? So they don't stay the same. Their position changes and so this is certainly moving azimuthally, right? Moving around in the theta direction. So there's V theta. So there's translation and rotation. Good. Remember that rotation is a deformation. It's really important that we not forget that. So just because the shape didn't change doesn't mean it didn't deform, right? Okay. So this form of solid body rotation we can think of as we think of, say, a car. So the car has wheels on the bus go round and round, right? And so each section of the wheel moves, right? And it doesn't deform as it does that in the sense of changing its physical shape. It's only rotating, right? So this one here, maybe another example would be like a record player. And so if you're standing here, you end up here, still at the same distance from the center. Okay, so this is solid body rotation. And this one here was an unusual example. Okay, what was the vorticity of this thing? Yeah, this was irrotation. So remember that this is omega. So this example here was an irrotational vortex. And if that hurts your brain, it should. Right? Because of course the idea of a vortex is trying to consider rotations of the fluid. But when we define the vorticity, which is, how do we define the vorticity?
Del cross U.
Del cross U. So it's a vector quantity. Okay, it's not just vibes, right? Oh, that kind of looks rotati-ish, right? There's a real formula here. And there's a couple different ways, of course, that we can make an irrotational fluid. What's the stupidest way to make an irrotational fluid? I see 3 irrotational fluids in this classroom. 4. Yeah, what about them as irrotational currently? Yeah, it's just sitting. The easiest way to make an irrotational fluid, the dumbest way to make an irrotational fluid, is to have U be 0 everywhere, right? That's obvious. Okay, it's not something necessarily that we internalize yet, but once you see it, you're like, oh, of course, my fluid not moving is not rotational. Good. And then there are other more clever ways to do it. So of course, we look at this thing and we say, well, this parcel rotates and deforms, so therefore it must have vorticity. But we calculated the vorticity and we found that it was 0. So in fact, we can have rotation and deformation be such that they counteract and we get no vorticity. Does that make sense? Okay. Everyone's brain's warm now? Oh, I forgot to clickety click. Clickety click. All right, so now we're really going to learn some hard math. Okay. All right. Put some words on the board that everyone hates. You like the Reynolds transport theorem? The what? So this is not work. This thing hates me. Okay, there we go. This is the Reynolds transport theorem. Okay, and I'm going to write it out for you, and then this is going to be a visual proof of it. We need this because we are thinking in terms of differential. So what I mean by that is we're gonna look at changes over time or changes over space. And we want to be able to relate them to our parcels. So let's say you start with some parcel of fluid and you're thinking about the changes to the fluid. So let's take that room that we were just in, and Kevin walks in through the edge of the parcel, which would be the door. Right? What has happened to the total mass in the room? You've added, it's gone up. So we need a way to talk about rates of change, differentials, and integrals over a surface. So things passing through some boundary. Does that make sense? And that's the motivation for this here. And it looks gross. I'll just say that. You know, some people don't like the way this looks, but it'll make a lot of sense. So we're gonna go ddt time differential between two times. So we'll say x, some position of at, right? Where some position a depends on t, and some other later position dt, also dependent on t, of some fluid property f. Okay? So this is, you know, arbitrary. We can treat it whatever we want. If you want to think that that's the density, or if you want to think that that's the salinity, those are all perfectly fine to hold in your head. But this is really equal to an integral between a and b of df dt dx plus db dt of f evaluated at b, and we're going to take away the other one, db, dA, dt, f evaluated at a. Okay. So can I prove this? So what have I said first? How do I say this first thing in words? Just the left-hand side. Good, so this is the rate of change between A and B, good, of function of x and z. Almost there. There's one more word I'm looking for. What does this thing do? What? What does the integral represent? Area under the curve. Okay, so what is this really saying on the left-hand side? This is saying that the rate of change of the area under the curve of the function f between points A and B. Okay, so I have some function f, and what I'm curious about is how that area under that curve changes with time. Okay, so let's have an example here. Here's f, and it changes. Okay, maybe it goes up. Okay, so this is the new f dx dt. Okay, so here's the thing I care about. This thing is the rate of change of df dt dx. Okay, here's a, by the way, the original a, and here's b. Here's a little bit extra called dA, and a little bit extra called dB, because remember we're doing this differentially. And we're gonna let a little bit of time go by, we'll call it dt. So this distance here, okay, this amount, is dA times f. And this one here is dB times f. Right? Okay, so let's see if we can add up these pieces and get the right thing. So this first piece here is this one, is it not? Wait, where did I put it? Right. This first one here, dBf, that's this. The second one is this. And this one here is the one on the left, or the right hand side left term. Okay. You don't need to memorize how to get here, right? You can accept the Reynolds transport theorem as your Lord and Savior, and it will get us to where we need to go. What this essentially means is if I am thinking about the rate of change of a fluid property, and I want the integral of that fluid property, then I can relate it to its evaluation at the endpoints and the rate of change of that property itself. Okay? The integral of that rate of change. Okay. Okay. Let's use an example here. Let's think about it really in terms of, oh, I didn't even draw it. Let's think about it in terms of our parcel. And so I've drawn a parcel sometimes as like a box in class with my hands, but you can make it an arbitrary shape. So we can make it this funny looking cashew, right? And you have some fluid in here. And the fluid is bounded by this beautiful cashew. And it has, of course, some area, some surface area that's not easy to calculate, and some volume that's likewise not easy to calculate. So as this fluid parcel moves through the fluid, maybe the jelly bean deforms or whatever else is happening. Maybe it stretches, it expands, all of the ways that we can think about deformation. You might have a new volume, which would be the original volume plus some delta t, right? And similarly, you might have the area be some new area plus delta t, right? Or the original area plus delta t. So then we can just think about the stuff that's going in and out. Okay. So for example, if you have some jelly bean, okay, and you look at the jelly bean and all of the properties are the same, they're all time and space, nothing to govern, right? There's no equations of motion to consider there, right? But if we go back to that example of, let's say this room is a container and someone comes into the room, then we have to be able to relate the fluid property to the thing that created the change. And part of that is passing through a surface, right? So we can think about the fluid equations in two ways. We can think of them in terms of differentials, and we can think of them in terms of integrals. So some fluid properties, right? For example, if there's fluid moving into the jelly bean or out of the jelly bean, that will be going through the surface, right? And so we'll need to do an integral over the entire surface to see how many things got in and how many things got out. And you're just doing accounting. You're saying, okay, 10 people came in, but 3 people left. So the total number of people that arrived are 7. Very good. Nice counting. Okay, but maybe you don't care about the total number of people. Maybe you really want to know like how many shoes were in the room, right? That you might not be able to tell from the surface itself. So you'd have to do a completely different integral. You'd have to integrate over all the shoes that are in the volume, right? A property of the jelly bean itself. Does that make sense? Okay, and we're gonna see that we're gonna have to like use both of these formalisms when we derive things like energy passing through the jelly bean versus the energy stored in the jelly bean itself. Does that make sense? Okay, good. Differentials tend to be easier to think of. They look nicer to your eyeball, and we can think of them in terms of rates. But of course, because of the fundamental theorem of calculus, these are connected properties, right? Rates of change and stuff moving through stuff, they're related by the Reynolds transport theorem, right? Okay. Can I show you this? Yeah. Okay, so we can use the geometric description. I don't think we should go through all of the math here, so I'm just going to show you the last part. Where let's imagine that we take some property of the fluid, and instead of it just being in one dimension, we can turn it into 3 dimensions. So we might be able to say something like this, ddt, the integral over a volume. Okay, and this is some volume at a time t. Okay. Of some fluid property. X here is now a vector. dv. Okay, so what did I say here? I said I want to know the rate of change of this fluid property throughout the whole beam. Okay. We comfortable with that? It's the same thing that we said before, but now in multiple dimensions? But yes or no?
I'm just wondering if you, like, there is one for a Y, if there is one for Z.
Yeah, you can write this in Y and Z. That would just be changing from x1 to x2 to x3, right? But when I write it in vector form, then I have to think about the volume that I'm thinking about. If, for example, my vector only had 2 dimensions, then this would be an area, exactly right. You want to think about the area over that 2-dimensional object. Okay. So now this is where it gets more fun and gets much more helpful. This is now going to be equal to the volume integral, okay, at some time t of, I can just bring this in, I'm going to make it a partial, df dt dv. And this is of that same x and t. Okay. I'm going to write it safe. You get it, right? So I brought the differential in. And now, of course, if you bring the differential in and you're doing it on both of these, you need to do the chain rule. So that's okay. We're not going to cry about that. But check this out. This is a star t. This is the area integral of a thing f of x t. That's the fluid property. B vector dotted into n vector dA. So what the fuck did I just say? What exactly is the what? Yeah, good question. That's a very good question. What is n?
So like normal to DA.
Yeah, the normal to dA. So maybe I'll pull this down a little bit. You see that? That's that other arrow. All right. So dA is that area of the jelly bean. And at every point on the jelly bean, you can define something called n. And it's always normal, it always points away from the surface. Minus n points in towards the center. Good. And B is some arbitrary direction. Right? B is just pointing. Perhaps it's directly with the normal, perhaps it's not. Some choice. So this part here has a dot product that says how much of B is inside of n. Because when they are misaligned, when B is like this and n is like this, what happens? 0. Very good. So let's take that first case. Let's make this 0 for a second and see if the left side makes sense with just this first term. In the case where B, whatever this B is misaligned with the normal, can I understand what's happening? So first let's think about, let's give this an example. Let's say that this fluid property is velocity. Okay, that's going to be the easiest one to think of. And on the left-hand side, what I'm asking is, what's the rate of change of the velocity over the whole jelly bean? Okay. This first one says, well, that's easy. I just take the integral of how much the velocity is changing with respect to time. as long as there's no velocity going into or out of my jelly bean. It's only moving along the surface of the jelly bean. You see? So this is telling us something really important. This is basically our accounting tool. On the left-hand side, we're saying how much of the whole volume is changed. And he says there's two contributions to that change. One is how the stuff inside changes with time. And then two, whether or not any stuff comes in or out. And that's all the changes I could possibly account for. There's no other way to make change. Is that fair? Okay. You like it? Boom, Reynolds transport theorem. Nailed it. Okay. Can mass be conserved? Can it be destroyed? Can it be created? What do you think about mass? I like it. Sometimes it's weird. Okay, that's good. A little honesty. Okay, let me ask the first question separately. A second question separately. Can mass be destroyed? No. Can mass be created? No. This is not a star. We're not doing nucleosynthesis. Okay, this is a fluid. Now, do fluids work inside of stars? Yes. Are we doing that? No. Okay. So let's just start with a very basic assumption. Let's just say the mass can't be created. If that's the case, can I use this to create a law that says that mass must be conserved when thinking about parcel fluid?
Count for the chain on the right hand side come from something.
Excuse me?
Because you can't have something.
You're talking about this or this?
The right hand side,
This one. So you're saying, what do I want to do with this?
you would have to find something that's equal to make up for like why it's changed.
Okay, so you're saying over here, if I see some change in the mass of the fluid, it has to be accounted for by someone going in and out of the box. Just like when Kevin walked in the room. Right? The mass changed only because he arrived. You see? He can't spontaneously arrive. There has to be a reason. I mean, I guess spontaneously, if I blinked really slowly, right, it would appear that way. But we watched it happen, right? So passing through the surface is the only way to bring mass. Okay. So let's see if we can work out a conservation law here. Okay. How would we state conservation of mass in English, by the way? I think we just kind of said this. Stuff can't be destroyed or created. The question here is, how did you write this over a control volume VT? And I think we're kind of getting to that already. Do we know what it means, a control volume? Have you seen the word before in the book? I've just been saying the word parcel, but a control volume is perfectly fine. We can use that terminology as well. So let me ask, we have this Reynolds transport theorem that I just wrote on the board, and I would like for you to write or to propose, you don't have to write it down. I want you to pitch to me conservation of mass. How should it be written? You can pitch it in upwards. I can write it down. Once I hit press. Okay, let's think again what it means in English. See if we can turn that into. Okay, that's a perfectly fine way to say it. The amount of something we have has to mean the same, okay? Let's take that a step further. Let's try to mathify it a little bit. The amount of something we have, what's the something? Mass. Okay, so the amount of mass we have needs to be good. Okay, so that would be a way of saying final is equal to initial. Is there a way to say that with differentials or integrals? Okay, so the change in mass over time must be
The same.
must be zero. So remember that when we're thinking now in terms of words, right? That if the differential is zero, that means that when I do the integral, that it must be a constant, right? Okay, so there's no change. Because the differential says what is the rate of change? If the answer is zero, then that would mean that there's no change in that quality. Good. So in fact, we can write it like this. Okay, we're going to take the left-hand side, and we're going to say d dt. That's the rate of change with respect to time. And I want to think about a control volume. I want to think about my jelly bean. How does it change over my jelly bean? So I'm going to do this. Okay, this is my jelly bean. And what do I put now?
Should have the mass.
Excuse me?
Like just consider mass for it. Instead of like X.
Okay. I don't hate that, but it's not my favorite. And I'll show you why in a few seconds. So my jelly bean is able to move, right? It's not a real physical thing. It's a concept. So it can expand and it can contract, right? It can rotate, it can deform in many different ways. So what is it that I care about not changing? Is it the total mass? Do I care about not changing the total mass? Yeah, that's the one we don't want to change. But this thing here that I have is going to multiply total mass by dV. What's dV again? Change in volume, right? So essentially, once I do this integral, it's going to be mass times volume. And that's not really what I wanted to conserve. What did I really want to conserve? You said it earlier. Just the mass. So maybe I need a property that changes with the volume. That when I do this thing times the volume, I'll get just the mass, right? What? The density is the right one here, right? Because if I think about the density changing over the volume, then the density accounts for the changes in volume too, right? So in fact, I need to write it like this, okay? And this can be a vector. Okay, so what's that equal to? You're not wrong, but you're not right. Think about it a little bit longer. What is it we're trying to do? Good. So let's go back one more step. What was the thing that we wanted to have? We said that the one in mass A to be equal to mass B or something like that. And then we took it one step further and we said that it has to be zero. So our statement, right, that the mass not change with time, right, means that this differential needs to be 0. Now, we are not precluding what you're saying, right, which is that this right-hand side still goes on that side. But what we're doing is we're sticking this statement in here, and we're giving it its own name. Okay, this is conservation of mass. Okay, now of course you're right. You know, you could look at this 0 and you could say, well, that must mean that this right-hand side is 0. No, it could be 0, right? Because what we have here is, let's change the volume. Let's change the mass inside of our jelly bean. There's 2 ways to do that, right? Okay, so here, the total mass can change. The density can change inside.
How if you're not adding anything except on the right side?
Ah, what does this thing do?
You're adding or taking away.
But you're adding or taking away, right? So how can I change this one? Let's make this one get bigger. What did we say about V and N, by the way? What happens when N is pointed in? It's negative. So if I want to add density to go in, then this is a negative. And this is a positive. And then they. Yes. So if I want to pull stuff out, then this is a positive term. But this is beautifully constructed? Yeah.
So we also write that as the integral of dot NBA.
The integral. So I might write this as like d rho dt dv plus rho b dot n dA. And so this whole side would equal 0. But I'm going to show you a nicer way to do it. Okay, because I'm a big fan of the continuity equation. Why is this not going? Okay. So, we can, let's go back. Wait, hold on, let me just write it just so you have it. Let's write this part first. So this would be equal to the integral v d rho dt. I'm not going to write it all of the what goes inside, but that's okay, right? Here's a rho u dot n dA. Now, why did I have a u there? Yep, but why did I add a u? Over there it was a b. Yeah, what is density? What kind of property is density? Mass per volume, so it's a scalar, is that correct? Does it have a direction? No. So how can fluid density, how can it get into my jelly bean? Yeah, it would have to have something that brings it in. The velocity is what's bringing in the density. Is this better? Is that what you're thinking about over here? Yeah, so that's how you would write the left-hand side. And it's still equal to 0. Both sides are equal to 0. Right? Okay, so so now I'm gonna delete what I just wrote, because I like this version better. It's in your book. This one is definitely in the book. I just read it out of the book. 4.2. Believe me, you will never trust Grismani to write down any equation from his brain. It's gonna have a minus sign in it. It's gonna have some v that's not supposed to be there. Okay. So instead, let's think about this in terms of the differential. Okay. So I can write it like this: d dt of a quantity rho plus del dotted into rho u. And that equals what? 0. That's exactly correct. This is called
Yeah, the little, can you put it down?
what?
It's because of glare, you can't really see the letters. Yeah, that's the mirror cover. It's the glare from the character.
This one.
No, right. In the parentheses.
Oh, rho times u. Rho times u. Oh yeah, it's super bright. What the fuck?
The glare.
I was like, what are you guys talking about? Keeps up with these shoes, good one. Okay. So this thing is called the continuity equation. You are going to see it a bunch of times because one of my favorite things to do now that you're learning the fluid equations is at the start of every lecture, we are going to define every equation that we found. And you're going to have to describe in words what it means. So let's try that here with a continuity equation. Okay? What does this left-hand side mean in words? The change in density with respect to time. Nailed it. Good. Not Kevin. What does this mean? The divergence of the mass. You're like 90% of the way there, but I don't think that you could tell your grandmother that and she would understand it. Is there an easier way for the class to understand it?
They've been changing I want to say like change space, but
And it's definitely a change in space, right? That's the del, that's a space changer. But that's also not what I would tell my grandma. You can't explain it simply, right? It means that you don't understand. So let's think back to what is the motivating factor. It's one event at the beginning of class. What? Kevin entering the room. Okay, let's explain that. Right? Because we can't make Kevin spontaneously appear. I was like, not a magician. There's no magic in this class yet. Okay. So Kevin appears. How did Kevin appear? What? He walked in. I think you're reading, right? I think you're reading what's up here instead of thinking about what we said, right? And this is gonna throw us off if we try to read it. But if we try to interpret what it means based on what happened, then we can ascribe it meaning after the fact. So how did we describe this first part? We said that this was. He appeared. He appears because. So the change in mass is here. Right? This is what happened. This is the change in mass with time. Because of. The velocity that brought him in here. I would say, maybe in simple words, he walked in. The mass increased because he walked in. Okay, so now let's mathify it up. Okay, he walked in, there was velocity that brought him through a boundary, right? He entered our control volume. By entering the control volume, the mass went up. Okay, so what this is what we call advection. You've seen this before, right? What was the advection from? Advection. Moving with flow? Is that what happened? Didn't he come in? The velocity brought him in, yeah.
So we're talking about was the amount of mass moving in and out of the.
Exactly right. So if we're thinking about some parcel, the amount of mass that flows in and out, when you add it all up, gives you the change in the density. So this one on the right-hand side, this is the advective term. And this one is the what's the professional term? Oh shit, pressure.
They're kind of steady.
That's correct. This is the steady or the unsteady term. Then I wrote that properly. So the left-hand side is the unsteady term because if it's non-zero, what do you know? The left-hand side. Yeah, if the left-hand side is non-zero, how would you describe them? That's mapping. You're right. You're right. But I'm saying, how would you just describe it in words? What does it mean when the left-hand side is non-zero? Something's increasing, right? So by definition, that means it's not steady, right? So just this piece gives us the hint as to what we call it. This is the unsteady term. We think about the word steady as being time changing, right? So this thing is changing with time. Density is changing with time. Good, unsteady. And then to your point, Kevin, it has to be counteracted by the cause, right? And because this thing equals zero, because of our continuity equation that we had earlier, we can of course relate those two changes. Will that be the case for every property? Like, are we just Gucci now that we figured this out? Yeah, right? Like, we're totally fine. There's nothing else in the world that isn't conserved, right? It goes in fluids. What are some other properties? So density. Temperature. Is temperature conserved? Oh, fuck. So in fact, this is the great starting point because the right-hand side is zero. But it's going to become more complicated once we have non-zero right-hand sides. Because I can't create this except for bringing it in. But what if there was a way to create temperature? Shit, then there's terms on that side, right? You see the future? Yeah, it sucks. Don't worry. Okay, so in fact, you've seen this format before, and you may recall it. So how do you write it? This format? You may have seen this thing. This thing? Yeah, what does that mean? Good, yeah, tangible system, good, good. How do you, what are the two terms that are inside of it?
Time space.
Good, and what are the two terms? You have your notes, right?
Oh, back into the.
I wanna know the actual ones, I wanna see how similar these two things look. Excuse me?
Speed of F equals del F dot U.
Okay, so I'm doing DDT is equal to partial t, is that what you said?
Oh,
Plus.
yeah, sure.
Plus,
Yeah, the del. Of that function, this one uses F but dotted.
okay, so let's do that. Like that? Okay, so we're pretty close. It's not exactly right though, huh? Tricky stuff. How do I get those two to look more similar? Well, first thing I could do is I could do something like this, right? Let's use row. And then this will be row, right? So pretty close, pretty close. It's not quite right though. What do we do? Two? Right, but this is operating on this, and then it's got that. Whereas this is operating on both of them. Let's write this thing. What is del dotted into row? Yeah.
And then scroll down, dot U.
Let's say both of those are change space. Can you do that? No, you would need to. That product is certainly in there. That's gonna distribute some stuff in some ways. You'll need a chain rule. Right. You like the chain rule here?
You can't do. Why would you do a chain not product?
You need product rule.
Because the chain, you use that if something's a function of the other, right?
Well, here the differential is DDX, right? These are both DDX. Potentially, and they're X and T. So this thing does the differential on this and leaves this unchanged, and then it does leaves this unchanged and it does the differential on that, right? Isn't that the chain rule? Was it the product rule? The chain.
The chain is like when you have a function f of g of x.
Good one, I don't want to, right? All right, so let's write this down then. So it's del of row dotted into U plus, and now I'm just gonna pull the row out, right? Row del dot U. Is that okay? Yeah, that's a great instinct, and you're like, what the fuck? Okay, so remember that del is an operator, right? It's gonna change some property. So here del only operates on rel. And then when you're done, you multiply it or you dot it into u. Whereas here, row is unchanged. And then you're just basically taking del dot u, which is only taking the operators of del that are in the direction of u. Okay. We can work it out on paper. It's much easier to do like 19 times, and then you're like, oh, okay. Right? It's like one of those things where like you have these vector quantities, and as you write them out, you're like, I actually see how they interact with one another, as opposed to just a bunch of letters on the screen. Okay, so now we're getting really close. So we had this continuity equation, and we had this so-called advective term and this so-called unsteady term. And the advective term we broke into two terms, right? And I was saying, damn, that looks really close to the total derivative. Excuse me?
Oh, for, can you try to change that second term? That looks like the total.
The one here? This is the total derivative.
Yeah,
Yeah,
but you
but
don't.
that's not what we have. There's two terms. Right? This is the unsteady and two advective. You like one of these terms being zero?
I was just gonna say they're the same, so the very last one is the one that's extra.
Oh, okay. So this total derivative, right, would be the continuity equation if we could make some assumption about the flow. We could say some special thing about the flow, then we could say that the continuity equation and the total derivative were the same. So that would require this term being zero. So there's only a couple ways to do that. Okay, can rho be zero? Well, technically it can, but it's really boring. It's not a very good flow. Good. So let's not have it do that. What about this one? Can del dot u be zero? In fact, it can. So del dot u being zero is something important. We call this the condition we're in wait, incompressibility. What are you talking about incompressibility, Monty? We're talking about density at all there. That's just v dot del or del dot v. That one's screaming. You should be angry. That doesn't make any sense. Right?
Well, means there's no, the view zero, that means there's no change on the volume, right?
Well, it's del dot u. That's zero. And I'm claiming that that condition means incompressible fluid. What does that mean, incompressible fluid? I just wrote it, but it can be deformed. It can be deformed. Because remember, a rotation's a deformation. And I can stretch it. And I can tilt it. I can do all sorts of fun things with it. So we need to be a little bit more careful here. Incompressible just means that it can't be what can be small?
Density does not change with pressure.
There we go. The density is constant. What? Delta U means the density is constant? Are you crazy, Krismani? Let's think about our example of Kevin. Kevin walked into the room. Right? The density went up. Passed through a boundary. We would consider, if we're going to be polite, that everyone in this room should be an incompressible fluid. Right? We do not want to walk into a place and be crushed. Okay? But imagine that you had some volume of air in this room. And instead of Kevin, you take a nozzle and you stick it in and you pump more air in. Right? Is air compressible? Famously compressible. Because it's in our tires. It's in our bike tires. It's even in the thing that we compress, like when you pump, you can sometimes use one of those like nozzles, air compressors. So gases can be very good at being compressed. But in order to do that, they need to change their density. Right? And in order to do that, this term needs to be non-zero, del dot U. Okay? So for a fluid, stuff coming in, right? We didn't talk about how, we talked about the density in the volume, but we didn't necessarily talk about the fact that you could change the density in a location. It's constant everywhere.
If you're maxed, if you're, like, you can no longer compress air, like at what point do you like say it's incompressible now? If like I have a tire, I'm inflating it, it's max, and I can no longer pump air into it, is that now considered incompressible?
When you say you can't, do you mean like the strongest man in the world couldn't, or do you mean like physically? Because think about what happens when you take an object, right, like a fluid. So take air, for example, and you take air at the same temperature. So let's take room temperature, and we keep increasing the pressure. We keep increasing the pressure. What happens? So we keep the temperature the same.
Oh. Expand, but I mean the tire would expand, but I'm thinking.
Sure, but let's imagine that we're in a lab. Okay, we have a lab. It's really state of the art. You have some big old tube. You get to look in. You start with air, and you start putting a ton of pressure. Air, without changing the temperature. Good. Which direction is it going? Have you ever seen the triple phase diagram? You guys seen this before? Starts down here, goes up, you have a little dot, then it goes like this. Okay. Do you know what these are called?
States, right?
Yeah, these are PT diagrams. Oops, that's not a row, that's a P. So pressure goes up, T goes that way. Okay. You live. What? Here? Where are we right now? I didn't draw any markings. You should be able to tell where you are because you have something in front of you. You have water, and water is in what form? Liquid. So you better be somewhere in here, right? Okay, so where is it? Let's say it's right here. Liquid form. Okay, that's for water. Okay, if I go down and I cool, it becomes a solid, and that's called what? What's the process called? Ice is right, but what's the process called? Freezing, yeah. It's so cold in here, it's freezing. Good. So that's freezing. What's this one? Vapor. Good. So this, by the way, is a. This one is a. This one is a. Good. This is freezing. This is Sure. Some people will say evaporation, some people will say boiling, right? Those are all perfectly good terms. Vaporization is the correct one. Good, now let's go up and down. Let's increase the pressure. Is it? Still liquid. Fuck. Decrease the pressure. You say solid or gas? Which one? Gas. So what is this example? If I go from here to here.
Same.
Yeah, it's still vaporization, right? Where does this happen in planetary science? Is that melting? Yeah, it's kind of evaporation like. Does this happen anywhere in nature? Not the place that you visited, obviously, because you would die, but not quite low enough pressure for that to happen organically. Not on Earth in planetary science.
These are fitting in.
Have like, those look like-
You could have low or high pressure. High or low? High. Yeah, going into space for sure. That one will fuck you up, right? But that's not the one I'm thinking of. Going down to zero, obviously, immediately.
Maybe the moon.
Moon has no atmosphere. It's basically zero. That's like space. What do I work on? Mars. Mars has 6/1000ths of our pressure. So not only can water not exist on the surface, if liquid water is present on the surface, it immediately evaporates unless it's cold enough. So here is where liquid water works on Mars. It can go between solid and gas in a process called sublimation and freezing. Sublimation, freezing. If you take a liquid cup of water from your spacecraft, bring it down to the surface, it immediately turns to gas. Okay, is that crazy? Okay, so let's go back to why we do this at all. This idea of compressibility. I add enormous amounts of pressure to the gas, and it stays fucking gas. How crazy, right?
I mean, yes, but I'm thinking. I'm like.
Yes, but no, I don't like it.
Like, depending on where you are along that line, like if you're at low temperature and you're at like right below the solid line,
Here,
yes, and you increase the pressure.
Yeah.
You're gonna see a solid, right? Or depending on where you are at the temperature, so if you like, I'm just thinking like you.
yeah, but remember, we started with the presumption that we were filling up a bicycle tire,
Oh, yeah.
right? So you're absolutely correct. You can think of some really fucked up things, right? So like you could start down here, and these, by the way, they're weird and they curve, and then this kind of like stops because it's like a sort of a poor description. So you could start down here, you could go through what would be a solid phase, and then it's in like a pseudo liquid later, right? Because it's really all about how are these molecular bonds interacting with one another. But yeah, this is a great line of thinking because you're not just thinking about fluids as being one type of object, right? Some things can have fluid properties, some things can have solid properties. Right? The best thing about science is as you learn more, it actually gets harder. Like you're like, oh, all those assumptions I made, those are wrong, you know? Okay. So this statement here, del.u, that is the statement of incompressibility. Okay. And this is the term here. This is the total derivative. These are fluid transport terms, both of these. Okay. The first one says, how does the density change in the direction of motion, so this is the advective term. And this one is the compressibility term. You see that on that? If you don't see it, you're gonna see it so fucking much, you're gonna get sick. Okay? And again, the goal of this class is not just for you to be able to memorize the symbols, but to be able to explain it to your cousin or your grandmother. Because when you can describe it easily, then you understand it well, right? So let's see if we can practice this over the next couple weeks, months. First term here is the unsteady term. Second one is the advective term. And this one is the, does that make sense? Okay, we'll do harder stuff. I think we're running out of time here. We have a few more. Oops. Can we defer this update, please? Fucking computers, piece of shit. Okay. Oh God.
I have a question real quick about that formula. You know how we mentioned temperature, like just the right hand side will be non-zero stuff? Why would you choose to do that, not just like change in terms of energy? Because you know that's conserved. Or you're just saying there's a way to do it?
Is energy conserved? What are you talking about? Is energy conserved? What do you mean? What do you mean? Let's imagine for a moment. You're talking big picture. I'm talking fluid. I'm talking about a parcel of fluid. So I know ways to get energy in and out of the system. Right? You're thinking all energy, certainly conserved, correct? I'm talking, can I heat up a fluid? Yeah, that's not energy conserved, right?
Oh, I guess it still would not be, okay.
Because there's a heat term. Now, when we talk about conservation laws, all we're saying is on the right-hand side, you have something, changes to the object. And on the left-hand side, they're due to these things, right? So for mass, changes to mass are due to nothing. That's what the first conservation law is, right? But for everything else, for momentum, for energy, we're going to later on get into like vorticity or anything else that we want to do. We're going to have changes to a property like energy is due to the fact that I heated it up, or the fact that it fell down a hill, or the fact that it did this, right? These are the changes, right? And then we move from the idea of kinematics, which is the discussion of motion, to forces, right? And once we have forces in our fluid, then we'll begin to really see how powerful this work is. Okay, so, shit, I just erased it. Well, you got it. 4.8, we can write it in terms of the total derivative. We talked about the density being constant, right? If the density is constant, then the total derivative is 0. That was a statement about incompressibility. In an incompressible flow, the density of the fluid particles doesn't change. Okay? But different fluid particles may have different densities.
Like how oil and water have different density.
Exactly. So you can think of it that way. You can think of them as completely separate fluids, right? You can think of one having the word oil and the other having the term water. But you can also just think about a flow in which multiple fluid densities exist. Is that fair? Okay. A fluid is generally considered incompressible when, Kevin said this earlier, the density doesn't change with pressure. Okay. Okay. You're gonna run into, and I'll just leave this here. So we're gonna use stream functions, and this is gonna naturally come out of the continuity equation. These aren't arbitrary tools. So make sure that when you're sort of rereading the section on the continuity, just go back and touch up on streamlines, stream functions. We're gonna use those to demonstrate. Okay. Comments, questions, concerns? Yeah.
So what happens if that's like less than or greater than 1 0? Like what happens to them? Yeah, what happens to your notes?
Here, this one?
Yeah, like if that's less than or equal to zero. Like, what does that tell us about them?
Yeah, so what this means, so let's say that's less than or equal to zero. So if it's equal to zero, that means that no flow was brought in. There was no changes to the density in the direction of the flow. So if it's negative, that means that flow left. U would be in the opposite direction. Right? Zero would mean, for example, maybe it has a jelly bean, right? And maybe there is flow, but maybe the flow goes around the surface of the jelly bean, such that no mass goes in or out. It just sort of rotates around the edge of the jelly bean, right? And you can imagine this in a sort of stupid way. Let's imagine, okay, not a jelly bean, but this really cool sweater, okay? There's like a big old clump over here and not so much of a clump over here. But, you know, let's say you can't see density in this example. Let's say the more dense part was moving, but it was moving along the surface, and the less dense part was moving along this surface. Still along the boundary, not through the boundary, but the mass distribution is changing, right? So in that case, this thing is still zero, despite the fact that the density is changing within the volume. But it's not aligned with entering or exiting the volume. That make more sense, Winston? And yeah, this first section, I think, you know, it'll be a little bit of a slow start, but once we really get using it, I think you'll feel more comfortable. Hopefully. I did my job, right?